the key item in the design of the camera is the lens. And I want to take a little time to talk about properties of lenses so you have some concept of how that works. So a lens is designed with a specific focal distance. So the idea is that if the light comes in a parallel beam, then the light beam will be focused at the position of the focal distance. So if you have the focal plane is parallel to the lens and at precisely the focal distance, then parallel beams of light will be focused precisely on that focal plane array. So how do you get parallel beams of light? Well, for instance, if you go out at night and if you ignore atmospheric distortions, you can approximate the light that comes from a star that's light years away as being parallel, because it comes such a large distance, right? So if this is a star that's light years away, if you're far enough away, so close to the source, it looks like a circle. And as you get further from the source, the plane wave becomes more and more parallel. And by the time it gets here, it almost looks perfectly parallel. So a source of light that's very, very far away and a point source of light that's very far away will produce a parallel beam of light. And that parallel beam of light then will get focused down to a point in the image that would be the point corresponding to your image of the star. And with a camera, you couldn't resolve any surface detail on the star. I mean, if you had a very high power telescope and it's a nearby star, I mean, perhaps you'd be able to see something, but or near a planet in the solar system. But for objects that are very, very far away, the angle subtended by the object is so small that it's effectively a point of light. Okay, now, so now what happens is that, of course, you're often imaging things that aren't infinitely far away or extremely far away. So in that case, the object distance is some finite quantity, and we'll define that as d sub o for the object distance. And then the focal distance of the image of the lens, that's a property of the lens, d sub f. So this is a property of the lens. The focal distance is the distance that you need to have the focal plane away from the lens. It's the distance to the focal plane when you have ideal focusing of an infinite source of light onto the plane. So this is a property of the lens. Now, in practice, the object distance may be less than infinity away, in which case you have to adjust the focal plane of the in order to get that object into focus. And the equation that describes that is right here. So if d sub I is the distance to the image plane, and d sub o is the distance to the object, d sub f is the property of the lens, the focal distance, then 1 over d sub o plus 1 over d sub I needs to be equal to 1 over d sub f. So let's say if there's some scenarios that you can consider to give you a little intuition. If d sub o is equal to infinity, then this equation is 1 over infinity plus 1 over d sub I is equal to 1 over d sub f. So that just reduces to 1 over d sub I equals 1 over d sub f. So that means that d sub I is equal to d sub f. So that's just what we had before, which is that if the object is infinitely far away, then it focuses at the focal distance. Okay. Then another possibility is that, but if d sub o is less than infinity, okay, then what would happen is 1 over d sub I is equal to 1 over d sub f minus 1 over d sub o. So in that case, if this is less than infinity, then this number is a positive constant which you subtract. So then d sub I, so that implies that d sub I is going to be, let's see. So if this is positive, so that'll make this smaller, and the reciprocal of a smaller number is larger, so that'll mean that d sub I is greater than d sub f in that case. Right. So as the object moves in, the image plane moves out, and the relationship is controlled by that equation. Now, what also happens now is that there's an effect of magnification. If an object has some particular size, then as you can think of it as sort of reflected through the lens. You know, one limiting case we'll talk about in a minute is a pinhole camera. So you can think of this as being a pinhole and the light rays pass through. And if the image plane is close and the object is far, then the image will be smaller than the object. That's the normal case that occurs with a camera, right? When you image a scene, the image on the sensor array is very small. So it might be a tree, but it's on the surface of the sensor array, it's very small. But in the real world, it's large, okay? So in this case, the magnification is less than 1. And the negative, well, in general, the magnification is a negative number because the image will be flipped upside down. But mostly, we're also concerned about the magnitude of this number. So if d sub O is much greater than d sub I, right? So the object is a lot further away than the imaging plane. So this would be like a camera. Okay. And in that would be like a point and shoot camera. So what would happen in that case is m here equals minus d sub I over d sub O. So this is so the absolute value of m in this case is much less than 1. So the magnification is less than 1 in terms of the magnitude of the magnification is much less than 1, and the negative sign indicates that the thing is flipped upside down. If, on the other hand, though, d sub I is much less than d sub O, see, that can actually happen, and in that case, m here is going to be equal to minus d sub I over d sub O is, so that's, in that case, the absolute value of m is much greater than 1. So in there you actually get positive magnification. So when do you think it is that you would get a lens? So here's the lens, okay? And here is the object. And then the image, the focal plane here. In this case, the focal plane is far away and the lens is close to the object. When does that occur? So I'm drawing a pretty bad version of this, but this would now be your eyeball. This is a microscope. In a microscope, you have to magnify the object a lot. So this lens has to get very close to the object you're trying to magnify. So this is a microscope. Okay. So both cases are useful. Also, you can buy cameras. If you buy an expensive camera, often it'll have the lens on it will have a what they call a macro setting. So in the macro setting, you can actually take pictures of very small things and have them magnified onto the surface of the lens, surface of the imaging array. So you can use your camera to take pictures of like insects or small animals or plants. Okay. And this just explains what I've just described in the notes. So for a typical microscope, you have magnification, and for a typical photography application, you have reduction. And here I should probably put absolute values in front of the m's, since it's really the magnitude of m that we're talking about here. The sign is always negative just because you get reflection, inversion of the image onto the surface of the imaging array. So now what happens is that this is a very important topic, aperture and f-stop. So the lens, in practice, a lens can only be made so large, and for lots of reasons, and we'll discuss them. And some of them are cost, some of them are limitations in your ability to fabricate, some of them are practical limitations, like you wouldn't want a large lens in your cell phone because it would take up too much space. But so in addition, usually there's some aperture that controls access of the light to the lens. And the aperture has a distinctive look to it in typical imaging, like cameras. And what happens is that it looks like this. There's like a set of metal thin plates that are designed to sort of overlay like this. Okay, it should be symmetric. So it should form a circle. And then as these leaves sort of slide in, they control the aperture. So it's almost a circular aperture. And inside here, the light can go through, and outside here, it hits the black metal plate. So by controlling this, you can open or close the aperture to the lens. And it's just like the iris of your eye. You know, if you go outside, all of a sudden you're blinded because there's too much light coming in on a sunny day. And then the aperture of your eye closes down. The iris, the muscle there, constrains, and it closes the light down, and it lets less light in, okay? So you'd say, well, why not always let the most light in? Well, there's various reasons. Sometimes you get out of the dynamic range of the sensor, like you would if you go outside on a sunny day. But there's other reasons to lower the aperture, and I'll talk about them in just a minute. So there's a concept of f-stop of a lens and aperture. So the aperture is the diameter of the circular opening in the lens. Usually it's approximately circular. So here you have this aperture here. This would be A, right? So the area is really going to be equal to pi r squared, which is pi, hold on for a second. So it's pi r squared, right? So r is equal to pi over d over 2 squared, right? So that's going to be equal to pi d squared over 4. So here it would be pi over 4 a squared. So the amount of light that is let in is proportional to this, the area. And so the f-stop n is equal to the focal length of the lens divided by the aperture. So that's the standard definition. I'll put a triangle here because it's the definition of the f-stop, n. And what happens is that if n is large, you're letting in, okay, if n is large, it means that the aperture has gone down. That means less light. And less light means that, well, what it really means is that when you go to take the picture, you're going to have, if you can let less light in, that you have to leave the aperture open longer. So the shutter speed has to be longer to compensate. So often this is described as being slower. Less light is slower because the less light you have, the longer you have to leave the aperture open. And if you have to leave the aperture open too long, then you get blurring in the image. So if you're taking pictures of sports photography or, say, race cars, you need a very fast aperture, a very fast shutter speed, okay? So this is slower shutter speed. So you need a faster shutter speed in that case. So in that case, what you'd want is you'd want a smaller f-stop. So let me do the converse here. So if you have n is small, then that implies that A is large, okay? And if the aperture is large, that's more light. More light means faster shutter speed. And they say that's a fast lens, okay? So a lens, so here would be some examples. If you had n equals, if you had, say, for instance, n equals 2.8, that's your f-stop. That's fast. Okay, lots of light. Oops, light. Okay, if you have n equals 5, that's slow. Not much light. Not lots of light. Now, the other thing that's interesting is if you look at this formula, the area is proportional to a squared, and n is inversely proportional to a. So light is proportional to area is equal to pi over 4a squared. So that's equal to pi over 4, and this is going to be df over n squared. So that's going to be equal to pi over 4 df squared times 1 over n squared. So the light is inversely proportional to the square of the f-stop. So if you go from if you have f, say, I don't know, you say f equals, I don't know, 3, okay? And you go from that to n equals 6. This is 4x the light. That's why if you buy lenses, what will often happen is that if you go up by they'll go up in roughly increments of the square root of 2. So every time you go up by the square root of 2 in the f-stop, or you go down by the square root of 2 in f-stop, you're going to double the amount of light. So an n equals 2.8 lens is much more expensive than, for instance, an n equals 5. So that would be about 2 f-stops, so about 4 times the amount of light. So people will pay a lot more money for that lens. Okay, so you say, well, now, is it always better to just have a larger f-stop or a faster lens with a lower f-stop? Do you let more light in? Well, the answer is it's not always better. There's some important trade-offs. Now, anybody who's a photographer, if you talk to a photographer and you say, well, is it better to have a larger f-stop or a smaller f-stop, or a larger aperture or a smaller aperture, they'll say, well, it really depends on what you're trying to do, okay? If you have a telescope, telescopes, the better the telescope is, the larger the aperture. That's why if you go to like a very, very, huge telescope, it costs many, many millions of dollars, they'll have a huge lens, okay? Or they'll use a lot of small lenses that they coherently integrate together, so it's effectively like a large lens. Why is that? Well, it turns out that this is the lens, okay? And this is the image, okay? This is the Fourier domain. I mean, I can't derive the equations for this, but they're actually not that complicated. So this, you can think of this as f of uv, and this is the space domain. This is image domain, and this will be f of xy. Now, the f of uv has to be interpreted, and the f of xy have to be interpreted as complex quantities because it has to be the electromagnetic, signal, which it would be like the electric field, which is a sign quantity. It can go positive or negative. An image normally only goes positive because you're taking the energy of the photons to actually form the image. But if you interpret this electromagnetic field as a sign quantity, as electric field, then this is the Fourier transform of this. So we all know that the larger, in the frequency domain, the larger the aperture in frequency, so this is f of omega, and this is, or f of f, and this is f, okay? The larger that is, the smaller the impulse function, right? So larger this way means smaller this way. So if we get, a large aperture here, we'll get a small impulse response here. Small impulse response means we'll get a sharper image. So by retaining more frequencies, we get a sharper image. So by this logic, the theory of electromagnetic propagation tells us that the larger the lens is, the sharper the image is. However, in practice, that's not always practically true. It's true in a huge telescope when it's been designed to be perfect or very close to perfect, but in a real camera, in a real imaging scenario, it's not always true. And there's two reasons why it's not true. There's two reasons why constraining the aperture can actually increase the resolution of the image. One is because there might be there's two problems. With large aperture. One is that you get distortion in lens. So as you get further out to the edges of the lens, there's more and more distortion in the lens. And two is that there's this other effect called depth of field. So the problem is this: as the lens gets larger and larger, it'll give you, if it's a perfect lens, it'll give you a sharper and sharper image, but only for images which are exactly in focus. If the image isn't exactly in focus, then you'll lose actually resolution more rapidly. And to see that, we can look at this diagram right here. Okay, so here, lens depth of field. So this diagram sort of illustrates conceptually, it's not a proof, but it just gives you a rough argument for how depth of field works. And this, if the image is exactly, this is the focal distance of the image. So this is the image is, imaging plane is some distance from the lens. And for this focal length of lens, then something that at this distance would be precisely in focus. So here you'd get the theoretical point spread function associated with the aperture. Okay, so which is the point spread function here, size is inversely proportional to the size of the aperture. A larger aperture here will give you a smaller point spread function, a sharper image. But if you deviate from that, then you'll lose resolution. So, and the size of the resolution you'll lose corresponds to the aperture blur you get in this diagram. So you have the following expression here, that the D here is the okay, so the point spread function C0 is the blur, okay? That's this quantity. It's the blur point spread size in the image domain. D is the depth of field, okay? And N is the fstop of the lens, and M is the magnification. So, the relationship is this, that d over c0 is equal to 2n over minus m. Okay, so what it means is that the depth of field is equal to 2n times c0 over minus m. So if you fix the resolution c0 and you ask what's the depth of field you get with that resolution, then the depth of field increases as n gets larger. So as n gets larger, remember, as n gets larger, the aperture gets smaller. So a smaller aperture implies that d gets larger. So a smaller aperture will result in a greater depth of field. That's why photographers will tell you that, let's say you have a lens that's n 2.8. You might actually want to use, even though it's an n 2.8 lens, you might want to make n equal to n8, an aperture f8. Or actually, the way that they write that, I don't know why, but they write f2.8. It means that the aperture is 2.8. So you might want to go to f8, okay? And f8 could give you a sharper image than f2.8 because the depth of field, because if the object's out of focus, it still stays pretty sharp over a wider range of depth of field. People also use this for artistic purposes. If you're taking a picture of a person in a background, and you have like a scene here, right? And you have there's a person here, okay? You want the person to be in focus, but you don't want the background to be in focus. You want the background to be blurred out. Then you want a wide aperture. You want say, f2.8 in that case, because then everything that you don't want to see is out of focus. If you watch cinematography, like movies, you'll see this all the time, where they'll use depth of field to control what you see, where the attention is focused in the scene. Okay. Now, if on the other hand, you have the person here, and you're at Mount Everest or something like that, and you're taking a picture, and you want the trees in the background to be in focus along with the person, in that case you want to use f8, because then the smaller aperture will give you greater depth of field, and both the person and the background will be in focus. Okay? So, okay.